today's video, we're going to talk about modular arithmetic, and this is on our road to the RSA encryption algorithm as part of the Discrete Mathematics course at Harvey Mudd College. This is a fundamental tool used in understanding numbers and being able to compute things like powers of numbers really quickly, or at least in terms of finding their remainders when you're dividing by certain numbers. So the definition here that we're going to be using is that if you have a positive integer m that's at least 2, and two numbers a and b, we're going to say that a and b are congruent modulo m if they leave the same remainder when you divide by m. So as an example, if you let m be 6, then 13 is congruent to 1 mod 6. And this is usually written as 13 with this 3 horizontal lines, meaning equivalent to 1 mod 6. All right. Another example is 12 is congruent to 5 mod 7. They both leave a remainder of 5 when we divide by 7. And we can also look at negative numbers. So for example, negative 3 is congruent to 4 mod 7. The remainder, when we divide negative 3 by 7, is actually 4, because negative 3 is negative 1 times 7 plus 4. We will recall that if you have a number a, then the remainder when we divide by a number b has to be a number between 0 and b minus 1, which is 6. And we actually talked about that in a previous video linked up here. Okay, so another way to word this that's equivalent, and that we actually bring up in the book that this series of lectures is based on, is that a and b are congruent modulo m if m divides a minus b. Okay, so I want to write a note here actually, that this is written as a is congruent to, I'll get rid of this. It's written as a is congruent to b mod m. Okay, and an equivalent way to talk about this is that m divides the difference of a and b. So let's actually make sense of this. So if we think, for example, of the number 13 again, it leaves the same remainder as 19 when you divide by 1, or when you divide by 6. They both have a remainder of 1. And their difference happens to be negative 6, which is a multiple of 6. So why are these two things equivalent? Well, if we think about numbers with respect to dividing by m, a would be q times m plus a remainder. Let's call the remainder r1. And b would be q times m plus another remainder. Let's call it r2. And these quotients should be different. We don't know what they are. Now, if it's the case that both these numbers leave the same remainder when dividing by m, then these two numbers here are equal. So the difference of these two would actually be q1m minus q2m. And we notice this is a multiple of m. So it's definitely the case if they have the same remainders that this condition is going to hold, that their difference is a multiple of m. And the same thing kind of works backwards. If the difference of these two is a multiple of m, then when we look at the difference of these two, we'll have this difference here, which has the factor of m, and then we'll have r1 minus r2. All right, but r1 and r2 are remainders when we divide by m. So they're numbers that are at least 0 and strictly less than m. And we're saying that their difference is a multiple of m. You can't take two numbers that are less than m and take their difference and get a number that's a multiple of m unless that multiple is actually 0. And so these two things would actually have to be the same remainder. So two ways of looking at the same concept. And now I want to play again with examples to get a sense, and then see some consequences of this. And today we're going to see some really cool consequences in terms of divisibility. So to start, I want to look at these two examples here. So 8 is congruent to 3 mod 5. Their difference is a multiple of 5. And 12 is congruent to 2 mod 5. Their difference is a multiple of 5 as well. It's 10. Now we might notice some interesting things with respect to addition here. So if we added these two things, we would get that 20 is on the left-hand side and 5 is on the right-hand side. And it happens to be the case that 20 is congruent to 5 mod 5. Okay, but is this going to be true in general? If we have this is congruent to this and this is congruent to this, then their sum is congruent to the sum over here? Seems like it's going to be the case, but we don't know right now a priori that's actually the case. More interestingly, something happens with the product. The product of these two is 96. And 96 is 1 more than 95, so this leaves a remainder of 1 when I divide by 5. Okay, and it turns out this is congruent to the product of these two, which is 6. So 96 is congruent to 6. Wondering if this happens in general. And you can kind of start to see why something like this would be useful, right? If we think about this number is quite large compared to this one. And so we're reducing to find out what the remainder of it is when we're dividing by 5 in a useful way. One particular way in which that's really useful is imagine if it's the case that products still hold up with equivalences modulo a given number, then we know, for example, that 8 is congruent to 1 mod 7, right? So we can use that statement again to then say that a squared is congruent to 1 mod 7 by multiplying both of these here. And then we multiply these two, we'd get 8 cubed is congruent to 1 mod 7. So this is very advantageous because if you ask me at the beginning of today's class what the remainder of 8 cubed is when we divide by 7, probably have to compute what 8 cubed is and not necessarily know that this thing would work. So let's actually see that this is the case, that when you have two things congruent and another pair of things congruent with respect to the same modulus, then you have this addition and multiplicative property. So these arguments are in proposition 18 in our book. And one of the first parts of it is it says that if A is congruent to A prime mod M and B is congruent to B prime mod M, where A prime, B prime are integers and M is an integer at least 2, then A plus B is congruent to A prime plus B prime mod M. Okay, so we'll use this characterization here saying that two numbers are congruent if their difference is a multiple of M. So let's look at the difference of these two. So A plus B minus A prime plus B prime is the thing we want to investigate and hope is a multiple of M. The only information we have is that by this, A minus A prime is a multiple of M, and so is B minus B prime. So it makes sense to bring those two together. So if we rearrange this, this is the same as A minus A prime, and then plus B minus B prime. Right? And since M divides A minus A prime, and B and M divides B minus B prime, we get that M divides this. I'm going to call this star. M divides star. So these two, the difference of these two is a multiple of M, and so we get our conclusion. So A plus B is congruent to A prime plus B prime mod M. Okay, so you can notice that the second condition in our theorem actually states that this holds for the negatives as well, and we can replace all of these things that we have here with negative options. So here we'd have A prime, or A minus A prime, and then instead of B minus B prime, we'd have a minus right over here. And we get the same consequence because M divides this and M divides this is going to divide their difference. And so A minus B is congruent to A prime minus B prime. Okay, great. So let's go on to products. Okay, so now let's move on to the product. So we're looking at the difference of these two expressions and wanting to know why this is a multiple of M if A is congruent to A prime and B is congruent to B prime modulo M. Now, using this idea, we have that M divides A minus A prime. So that means that the difference of A and A prime is a multiple of M, maybe M times Q prime. So we can use that somehow to simplify this expression and hope for the best. And the reason to do this is because in our previous proof for why the sum of two things is congruent to the sum of other two things, we factored somehow this expression, and that's not necessarily clear to see how to do right off of face value. Okay, so let's do that. We'll say since M divides A minus A prime, there is an integer, let's call it Q1 maybe, such that A minus A prime is Q1. Similarly, you can do the same thing with the B's. There is an integer Q2, Q1 times M, sorry, because their difference is a multiple of M. There's an integer Q2 such that B minus B prime is Q2 times M. Okay, and so we want to know what the difference of these two is in terms of being a multiple of M. Hopefully, we can make a substitution in here that'll help us. So, AB minus AB prime, or A prime B prime, is we can make our substitutions for A and B. A is this A prime plus Q1M, and B is B prime plus Q2M, and then we're subtracting A prime B prime. And now we see the first factor here is A prime B prime, which cancels with this thing. And so we're going to be left with A prime Q2M plus B prime Q1M plus Q1 Q2M squared. Okay, and this thing here actually is a multiple of M. So I'll introduce this and say, so M divides AB minus A prime B prime because this quantity actually is this expression, which is a multiple of M because it's a sum of things that are multiples of M. Great, so we get this product thing for free, which is excellent. And now we move on to the last thing that we state. So this thing should have been numbered number 3, actually. It's the third thing in that proposition 18. And the last thing in proposition 18 is this fourth statement that says the following, that for any positive integer k, A to the k is congruent to A prime to the k mod M, knowing that A and A prime are congruent. So let's think about this concretely from our experience. So we know A is congruent to A prime, and we can write that statement again. Now, by what we just proved, if we have this, then the product of these two is congruent to the product of these two. So A squared is congruent to A prime squared. Okay, but we can continue. Now the product of these two is congruent to the product of these two. So we get A cubed is congruent to A prime cubed. And we can continue further along as we go increasing this exponent by 1 by using this and this thing right over here. Okay, but to give a solid proof, we can do this using mathematical induction. The idea is using this right over here repeatedly with what we had before. Okay, so let's actually write this in that form. So we'll say we proceed by induction. So when k is 1, we get the result for free. It's in the assumptions. So the result is given when k equals 1. Assume it's true for some k, then that means that A to the k and A prime to the k are the same mod M. Since A is congruent to A prime mod M, we can use the condition we just proved before. This is condition 4 now, so we can use condition 3 that we just talked about earlier. 3 gives A to the k times A is congruent to A prime to the k times A prime mod M, i.e. A to the k plus 1 is congruent to A prime to the k plus 1 mod M. Great. So we can add in a concluding sentence here if we had the option. We say then by mathematical induction, this thing is going to hold regardless of what k is. All right, so cool. So we have these facts about modular arithmetic. Let's actually use them to do some interesting things and interesting computations. So here's an example, a prototypical example of the type of thing that modular arithmetic can help you do that seems kind of daunting at face value, which is what is the remainder of this number here, 11 to the exponent 320, when it's divided by 9? So we'll make the first observation that 11 is congruent to 2 mod 9. Okay, so now, by what we just proved earlier, if we square this, it's going to be congruent to the square of this modulo 9. And that is 4. So we can replace this 2 squared with a 4 and say this. Now, the first question we should ask ourselves is, why are we even looking at modular arithmetic type things to begin with? Well, we talked earlier about the fact that if you have this number and you find another number, b, that's congruent to it, mod 9, then they leave the same remainder when you divide by 9. So for example, the remainder of 11 squared when it's divided by 9 has to be 4, because these two things are equivalent. And the remainder when 4 is divided by 9 is 4. Okay, so now let's use our product property. The product of these two has to be congruent to the product of these two. So 11 cubed is congruent to 2 times 4, which is 8 mod 9. Or in other words, when you take 11 cubed and divide by 9, you get a remainder of 8. It's already cool to know that that's the case like off the bat, because we don't necessarily know what 11 cubed is. Now we can actually simplify this further. Notice that 8 is congruent to -1 mod 9. Their difference is 9, and that's a multiple of 9. So 11 cubed is congruent to -1 mod 9. Why is that helpful? Well, one thing is we can square both of these now by our fourth property that we proved and get a power of 11 that's 1 mod 9. And that's going to be useful for computations because we can keep cubing it, squaring it, taking different powers, and the 1 won't change. So in particular, if we squared both of these, we would get 11 to the 6 is congruent to 1 mod 9. Now this might look fishy to you, because you might think, well, this is not a remainder when you divide this by 9. But it didn't need to be a remainder. Two numbers are congruent mod m if their difference is a multiple of m. And this statement is saying that the difference of these two happens to be a multiple of 9 that we deduced by all of these previous computations using the properties that we figured out earlier. All right, so I want to put this in a box right over here and then think about the implications using what we've already determined right over here. So the thing we're interested in is 11 to the 320. All right, so 11 to the 320 can be represented as 11 to the 6 raised to a very large exponent times 11 to something smaller. If we took 320 and actually divided it by 6, we would get something like 53 and a remainder of 2. So this can be represented as 11 to the 6 to the exponent 53 times 11 squared. Okay, so if you look at this number right over here, you can write it as 11 to the 6 times 11 to the 6 a lot of times 11 squared. And so if we apply the product property of congruences, this thing is going to be congruent to, because 11 to the 6 is congruent to 1, 1 times a bunch of 1s times 11 squared mod 9. And this is much easier to work with. 11 squared is the total product here, and that's 4. So this is congruent to 4 mod 9. And so we get that the remainder, when you divide this number by 9, is 4. And we figure this out all by doing these computations reducing modulo 9. So this is an example of the great advantage of having modular arithmetic at our disposal. Now, where this actually comes up in the RSA encryption algorithm is things are going to be encrypted in exponents of numbers. We're going to take a code or a secret message we want to send, turn it into a number, and then the way we're going to encrypt it is by raising it to a really large power and reducing modulo a number. So that'll transfer to a number that we send in our encryption algorithm. And we'll see how through various properties we learned earlier, or we learn later, is we're going to be able to decrypt doing that. Okay, another thing I want to mention is there's a curious property that you can find a power of 11 to get 1 mod 9. And that was really the thing that helped us be able to simplify all of this computation. We're going to see later for many values of pairs of numbers, like 11 and 9, there's going to be some exponent we can raise this 11 to get 1 mod 9, when we replace 11 with some actual number and 9 with some actual other number. That property is going to be discussed in a couple of videos from now. Okay, so now I want to take a look at divisibility properties in general and how you can learn whether or not a number is divisible by 9 from its digits and use modular arithmetic to understand why that property works. So here's a curious way to tell if a number is divisible by 9. It's a divisibility rule that says a positive integer is divisible by 9 precisely when the sum of its digits are. So for example, if we take the number 3951, when we add its digits, we get a total of 18. And so because 18 is a multiple of 9, this original number must be a multiple of 9. That's what the rule is saying. So what I want to do is investigate why this rule actually works using our modular arithmetic. For example, let's say our number was just randomly chosen to be 486. Now 486, we have 3 digits, D2, D1, D0. But the actual number itself is not the product of these. It's 10 squared times D2, 400, plus 10 times D1, plus D0. So if the number n has a bunch of digits, let's say dn, dn minus 1, etc. up to D0, so this is the number that we have it written in this form, then the number n itself is actually dn times 10 to the n plus dn minus 1 times 10 to the n minus 1, etc., up to 10 times d1 plus d0. Okay, so let's look at one of the summands here, d sub I times 10 to the I. Now since 10 is congruent to 1 mod 9, by applying our powers rule, 10 to the I is congruent to 1 to the I. Okay, and di is congruent to itself, mod 9. The difference between di and itself is 0. That's a multiple of 9. So this quantity here is actually congruent to di times 1 to the I, or just 1, mod 9. Okay, and now by our sum rule, if we apply this to every single one of these pieces, we get this thing is congruent to dn plus dn minus 1 plus up to d1 plus d0 mod 9. Okay, so why is something like this useful? Well, now we've said that this number n, which is this number here, is congruent to the sum of its digits modulo 9. The only way n is divisible by 9 is if this expression is divisible by 9, and vice versa, because if one of these is a multiple of 9, and we're saying that they're congruent mod 9, which means their difference is a multiple of 9, then the other has to be a multiple of 9 as well. So a cool way to prove this property that you may have seen in the past, but doing it concretely using this modular arithmetic framework. Great, so now we know how to exploit divisibility using this modular arithmetic framework that allows us to do calculations, especially with powers and products of large numbers, understanding divisibility and remainders. In the next video, we're going to continue combining this with our GCD work to understand how to solve what are called linear congruence equations.